Okay, we're going to continue on here. We're going to roll through the rest of 3. We'll roll into some 4. Then we'll roll out of here for the weekend, I think. Bless you. So last time we were talking about a couple things. We talked about sort of formal charge and how to calculate formal charge. Remember, to calculate formal charge, it is the number of valence electrons in the free atom minus the number of non-bonding electrons minus the number, minus half the number of bonding electrons. So the idea of formal charge, as we talked about, is it really allows us to sort of understand the charge that a particular atom is taking on as a result of it being bonding and sharing electrons in a covalent bond. And we could also use it to really help us determine between different sort of structures, which one may be a better Lewis structure versus another sort of structure. And we did a couple of examples of looking at different structures and different ways to put things together, and using the formal charge to help us do that. Remember, that's sort of the best situation in terms of formal charge, if that is something you're looking at in terms of drawing Lewis structures, is one where you really minimize sort of the formal charge on everybody, get everybody to 0. That's really optimal. If you can't, then if you get a lot of guys to 0, other ones to sort of a lower number. And again, if you have sort of an even distribution of a formal charge, like a -1, a +1 situation, you would want the more negative formal charge to be on the more electronegative atom. This is not the hard part of the class, like passing the roll sheet, right? All right. So not sure what's going on over here. So you want the more negative formal charge to end up on the more electronegative atom. Again, that makes sense because electronegativity is the ability of electrons to come towards an atom, basically. And that would mean the more electronegative guy really shouldn't be drawing those electrons closer to itself and becoming more negatively charged. Typically, large formal charges are not really good and sort of plausible. So if you end up with things like +2s, +3s, or 3s, I mean, there's pluses but minuses as well, 2s, 3s, and beyond, those are probably not the best structure for those guys. We then sort of finished up, I think, talking about this right here, which is bond energy, or bond enthalpy is sometimes referred to. This table, again, is the bond dissociation energy. It is the energy required basically to break or really even make different types of bonds, a single bond, a double bond, or a triple bond. Be different in terms of the energy required to do those. And the general trend that we do see is a double bond is stronger than a bond. A triple bond is stronger than a double bond. And also the distance between the atoms when we start making bonds does get a lot shorter. Everybody kind of moves in as we make the double bond and triple bond that occurs. So really, when we do this, the breaking of bonds, as we talked about, is endothermic. So basically what you want to do on the reactant side, thank you, is basically figure out, how many bonds you are breaking and what type of bonds you're breaking. So a very common mistake a lot of people make when they sort of do these type of problems is they don't really sketch the Lewis structures, and they really miss bonds, or they get the wrong type of bond. They grab a single bond versus a double bond or a triple bond. So sometimes it's easier just to kind of sketch everything really quickly, and even if it's not complete with all the dots and everything, but if you get an idea as to what bonds you're making and breaking, you obviously can get the right things. So because they're endothermic breaking, all the values that you would add up would end up being a positive number. Making is actually exothermic. Energy has to be released. So you basically do the exact same thing on the product side there. And since it is going to be exothermic, you basically just turn all those numbers into negative numbers. And to figure out the delta H of the reaction based off of that, you basically just add those together. So you add all the energy to break plus all the energy to make, and it'll give you, again, an overall delta H value, which, again, if it is a positive number would say overall it's an endothermic process that's occurring based on bond energy. And if obviously you got a negative value, it would be a exothermic one. So for example, here you can see they did it here. They added up all the bonds that were broken. So that's our probably H single bond here, our oxygen double bond there, for a grand total of positive 934 for the breaking part of it. On the other side, we had a couple of hydrogen oxygen bonds. And as I might have mentioned before, sometimes the benefit of drawing out the structure is, in a case like this, if it was just sort of the formulas given to you in like an equation, a lot of people will catch this bond and this bond, but it's a very common thing people miss, like the oxygen bond. So again, if you visually see it, you might not miss it. And that obviously will be that number right there. So it's going to be all negative. I'm sorry, that would be negative. And then when we add them together, we got an overall here of a negative delta H. Any questions on that there? So we talked a little bit about resonance structures as we were drawing Lewis structures, but occasionally you do come across what I refer to as resonance structures. And oftentimes it comes across when we're dealing with something that we are making a double bond with. And in a situation where we have maybe a multiple locations as to where you can make that double bond. And basically you could draw several different Lewis structures that are equivalent to each other. Carbonate, as we'll see here, and we talked about, is an example of that. Again, as you go through carbonate here, drawing it, you are short and you do need to make a double bond. And you could double bond over here to this oxygen, you could double bond to that oxygen, or you could double bond to that oxygen there. And because really those double bond electrons are what are referred to as being delocalized, they're essentially kind of traveling, if you will. So at any given point in time, they may be at any of those oxygens. So one Lewis structure by itself doesn't sort of adequately describe what's going on there. So you can draw several individual Lewis structures. They're usually separated by this arrow that's kind of heading in both directions to indicate they are resonance structures of each other. Do you need to draw resonance structures all the time? You do not, unless it specifically asks you to draw like all the resonance structures. If you just draw a legitimate one structure, that's good. That would be good in a situation. So ozone, for example, you could draw a resonance structure here. We could have double bonded there to the left, and we could have just as easily double bonded there to the right. The pluses and the minuses are the formal charges that were calculated here for ozone in this particular case. And then there's our carbonate that we talked about. And again, the true structure here is probably somewhere between all three of those sort of structures. In this case, I didn't put brackets because I included the formal charge on the actual elements. As we talked about things with charges, you should include the brackets if you're not going to include where those charges are. So again, this would be the proper way here to sort of do that. Benzene is an organic compound. It actually is 6 carbons, looks something like this. If you take organic chemistry, you will draw it nonstop. Actually, all these guys here are carbons. All these points. And they all have one hydrogen happening here. So benzene is a 6 carbon ring structure in organic chemistry, has 3 double bonds that are happening inside. You could draw a resonance structure where we just kind of double bond to the other side here. I'll do that that way. And a lot of times, or sometimes in lower level organic type books, they'll just draw this like a little circle in the middle to indicate that those double bond electrons are basically kind of moving around and could be at any particular place. So speaking of, and we won't look at this one, but speaking of sort of resonance structures are, you know, using resonance structures never mind. We'll get to that in a second. I had like a momentary loss of thought there, and try to get my thought back here as I'm just scrolling through. We'll get to it here, I think. All right, let's talk about exceptions to the octet rule. I don't know. It's Thursday. Don't worry about it. I'll be okay. I found the building. I think I know where I parked. I'll be okay. So let's first talk about some exceptions to the octet rule. So although up to this point, a lot of times they beat into your head that you obviously should always have 8. 8 is the magical number. There's actually a lot of exceptions to the octet rule. And specifically in this class, we do come across some exceptions that we will see a lot. So let's talk about some different ones. The first exception to the octet rule is one that's referred to as an incomplete octet. And an incomplete octet means that it is something that is actually perfectly fine with less than 8 electrons around it. A beryllium hydride, for example, there has only 2 and 4 electrons. I would say in most cases, it is boron that we see that the most of, boron here. So boron trifluoride here has only 2, 4, and 6 electrons, and it's actually perfectly fine that way. These type of compounds are sometimes referred to as being electron deficient, as they are obviously short some electrons, but they're actually okay. For the most part, if you were coming across an exception, probably anything containing boron there in the central atom would be that incomplete octet that you would come across and see. So usually it's group 3, and if you look at group 3, boron is kind of the only non-metalish guy that we got going on there. Aluminum as well is sometimes included in there, but again, aluminum, even beryllium are metals, and metals and non-metals tend to make more of an ionic compound. So here in sort of covalent bonding, it's usually boron that sort of is the one that we see a lot with the incomplete octet. Another exception to the octet rule is an odd number of electrons. And an odd number of electrons is pretty much what it sounds like. When you add up all the numbers, you got like 1 extra electron hanging out. So it is something that cannot pair off. And NO and NO2 are examples of that. The NO here has an unpaired electron there. The NO2's got an unpaired electron over there. Maybe you've heard of free radicals. Those are guys with unpaired electrons. Because they have unpaired electrons, especially a lot of chlorine molecules up in the atmosphere basically do that. They're very, very reactive because frankly, they don't really want the unpaired electron. They kind of want to pair off and stuff like that. So these things are usually very, very reactive. So I would say out of the 3 exceptions, that's probably one we come across the least would be the odd number of electrons. The incomplete octet does pop up with boron occasionally. But now the third, and really the one that we see the most in this class, is our good friend, the expanded octet. The expanded octet is pretty much also what it sounds like. There are certain elements that are perfectly fine going above 8 electrons, upwards of 10 to 12 electrons around it, and they will be fine. So some molecules can go over that 8. It usually happens if you look at the periodic table and you find your friend sulfur. And if you find your element sulfur and you kind of go to the right a little bit, go to the left a little bit, and kind of come down on the periodic table there, that is really where the expanded octet can really start to occur. And that is because sulfur, as I blind myself looking at that periodic table, I think it's still on period number 3. Now I can't see anything. And period number 3 is really the n equals 3 level, right? And on the n equals 3 level, what orbitals do we got going on there? There are s orbitals, right? There are p orbitals, and the other orbitals on the 3rd energy level are the d, right? That is where the d orbitals really begin. And that is why those that are at sulfur to the right, to the left, really the nonmetals to the right and left and down, can do the expanded octet because they pretty much have the d orbitals to house them. So they got somewhere to kind of put the extra electrons, and they're able to sort of do that because they have that d orbitals available to them. That also means, though, that if you go above sulfur, period, carbon, nitrogen, oxygen, and those guys, that is period number 2 on the periodic table. And period number 2 is n equals 2, where we only have s and p orbitals available to us. And that means that under no circumstance should carbon, nitrogen, oxygen, or any of those guys go over 8, because they do not have anywhere to store those electrons. So that's why it's basically sulfur left and right and down has the ability to do that, but anything above it in terms of the period there can never do it and should never go over 8. So SF6 here is an example of that. If we count up our electrons here, we have 6 plus 6 times 7, like a 48, I think. We're going to do a sulfur in the middle, and we actually will have 6 fluorines attached to it. 1, 2, 3, 4, 5, and 6. And obviously we would fill up our outside guys here. And obviously, as we can see here, 2, 4, 6, 8, 10, and 12 electrons around the sulfur, and it's perfectly fine doing that. So certain cases, we will see the expanded octet. In the next chapter here, we're going to talk about, we will see it with more geometries that go along with the expanded octets, which are not fun, but we'll see those. But some can do it and some cannot. Any question on those? So you do need to know the 3 exceptions to the octet rule. And again, like I said, expanded octet for sure we will see a lot, followed probably by the incomplete octet, and probably not too much, like I said, of the odd electron molecules. Any questions on that there? All right, so now to my previous thought there. If we think about sort of the expanded octet, right, and something that we drew before, which is sulfate. So we did draw sulfate, I think perhaps before, or maybe not, but if you did draw sulfate and you followed our rules for showing sulfate, you'll end up with a picture that looks something like this. Now, perhaps if you, I don't know, Google the answer or question of sulfate, which I'm sure nobody would ever do, you might come up with a structure that looks like maybe this. And if you did that, say, in your previous class, clearly your teacher knew you did that and Googled it, because you didn't talk about expanded octets, and you shouldn't be drawing anything that looks like that, by the way. But this would be an expanded octet that has 2, 4, 6, 8, 10, 12 electrons around it. So they're both sort of acceptable structures here for sulfate, because sulfur can go obviously to the expanded octet. We can, again, at this point, use our formal charts to help us decide which one would actually be a better picture here, or maybe a better Lewis structure. So if we did our formal charge for our single bonded oxygen like we've done before, that would give us 6 minus 6 minus 1/2 of 2. And that's going to give us a -1. So each of these single bonded oxygens in our sulfate that we would get from just kind of following our steps would be carrying a -1 formal charge. The sulfur here in the middle got some single bonds going on, which if we did the formal charge for that guy would be 6 minus 0 minus 1/2 of 8, and that would be a +2. So once again here, our sulfur in the middle has a +2 formal charge. We got -1s on the outside. It does add up to -2 overall for the charge. So, you know, it is a sort of plausible structure, or a structure for sulfate. If we move over to the guy on the right and calculate the formal charge, once again, for our single bonded oxygen, it will come out the same. 6 minus 6 minus 1/2 of 2 gives us our -1. So we got our -1 here, our -1 there. If we did it for our double bonded oxygen, 6 minus 4 minus 1/2 of 4 gives us 0. So this would be 0, and that would be 0. And lastly, if we did it for our sulfur in the middle with its expanded octet bonding happening That would be 6 minus 0 minus 1/2 of 2, 4, 6, 8, 10, 12, which gives us 0 as well. In this particular case, which one would actually be the better Lewis structure based on formal charge? It actually would be the one where we went with the expanded octet in this case. We actually minimized the formal charge on sulfur for sure. Sulfur in the first one is a +2, which is kind of iffy in terms of formal charge. We really don't want 2s and 3s. Is not really the best situation. Here, by actually going to the expanded octet, we're able to bring that down to 0 and really minimize it. And it would be the better structure, actually, the one on the right. Any questions on that there? All right, so again, use of expanded octets where, again, it can bring out perhaps a better structure based on formal charge. And another way you could, again, use formal charge to help you decide. Any questions on that stuff there? Okay, so let's take a look at some others here, I think. So why don't we draw a few more expanded octets here or exceptions? Why don't we try PCl4 minus XeF4, and let's do PCl5. All right, draw some Lewis structures based off of those guys there. Okay, let's take a look, see how we're doing. So really here, we'll just follow our same steps and see where we get to. We're gonna count up total number of valence electrons. So we got 5 for the phosphorus. There's 4 chlorines, each at 7. Here we do have a negative charge, so we do need to add 1 to it. So that's a lot there, 28, 29, 34, I think. So at this point, we're going to put the phosphorus in the center. We're going to do a little chlorine around. We're going to do a single bond to each of the outside ones. That is going to use 2, 4, 6, 8 electrons. That's going to give us 26 more to go, I think. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24, and 26 here. I feel like I miscounted here somewhere. I probably did. So over here, we have 8 times 4, which is 32, I believe. So we still have 2 more electrons to go. And at that point, we have nowhere else to put it. So we would just put it right there on the center atom as, again, a pair of dots. This is phosphorus, which is right next to sulfur on the periodic table. So again, it's that period 3. It has the d orbitals to allow it to go above. And it has, at this point, 5 electron pairs or 10 electrons around it. Any questions on that one there? Looking at the next one, which is xenon, that's actually group, yeah. So if you created a double bond, you mean just leave it the way it is and double bond with the chlorine there? Yeah, you probably wouldn't do that again in sort of the same situation. You would probably want to save double bonding to the end if you needed to. So you want to kind of get all your electrons first before you kind of go into double bonding or triple bonding in that case. Chlorine could technically take it because it is also on the period 3. Right. So again, that probably in the end may not be the best, or maybe it would be minimizing it. But usually you want to kind of distribute all electrons first and then kind of go into double bond or triple bond. Other questions? And again, if you were doing something where you're trying to figure out maybe based on formal charge, you could try things like that and see if it did help in terms of formal charge. If you're just drawing sort of Lewis structure, that's sort of the process there. You want to kind of distribute all the electrons first and then kind of go at that point. Other questions? Yeah, so we bonds that are not part of bonding, right, as dots. So in this case, this is really non-bonding electrons at this point, right? It's not part of a bond. By putting the line in there, that would then obviously make it more of a bonding electron. So at this point, it's really sort of non-bonding electrons that would be distributed basically as dots in this case. And probably even if you kind of went through this process, you would end up with this, and maybe see if make it a double bond by bringing those dots in to make the double bond would probably be the better approach than just kind of double bonding at the end. Other questions? Okay, so next one is xenon, which is 8. 4 times 7 is 28. So 28 and 8 is 36 in this case. Here we're going to put our xenon in the middle because fluorine will not go in the middle, and plus xenon really has no electronegativity value. And here we will go 1, 2, 3, and 4 in this case. That is 8 electrons. So we'll fill up the outside 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24 there. So at this point, once again, we've distributed 32 electrons. So here we will put it as 2 sets of dots there on the central atom, or 2 pairs of dots on the central atom, giving us our 36 electrons. In this case, xenon again has obviously 12 electrons around it, 6 electron pairs in this particular case. Other questions on that? Lastly, here we have phosphorus, which is 5, chlorine, which is 7, and there's 5 of them. That is 40 electrons. In the middle, we'll go phosphorus. We'll do our chlorines on the outside here. And again, we'll distribute our electrons on the outside. And I think once we get through here and fill it up, that now should be 40 electrons, and the phosphorus again has 5 electron pairs, or 10 electrons in this case. So again, even with these sort of expanded octets in general, if you draw Lewis structures, you do want to sort of distribute the remaining electrons as electron pairs as dots, because they're technically non-bonding electrons. There's no atom that you directly bonded it to, and that's why we kind of go in that order where we bond out first to everybody that's there in terms of atoms, and then we consider pretty much everything else to be sort of non-bonding electrons, and then we want to kind of distribute all those first, and then at that point, if necessary, you could do some double bonding and triple bonding. Any questions on that there? Any questions on drawing Lewis structures, expanded octets, exceptions to the octet rule, Lewis structures in general? All right, so that wraps up that part of this chapter. I think what we have left is just naming. We'll come back to that. We're going to go to chapter 4 now, and basically kind of continue on and talk about. So this is the next third chapter, although it really is sort of a continuation of what we've been talking about, which obviously is Lewis structures. So in this chapter, we're going to talk about geometry. We're also going to talk about hybridization, and we'll talk about molecular polarity here for atom or molecules that have 3 or more atoms involved. We're talking about molecular geometry, and as we go through molecular geometry, there's really going to be sort of 2 types of geometry names that we're going to talk about. One is sometimes referred to as the electron pair geometry, and that sort of describes how the electron pairs and are arranged around the central atom in 3-dimensional space. The other type of geometry we're going to talk about is the molecular geometry, and that is also sometimes referred to as the shape of the overall molecule. And as we'll talk about, depending on the type of electrons that are involved and what types of electrons are around the central atom, the overall molecular shape may change a little bit from the electron pair shape, as ultimately the basis of this, as we'll talk about, is there are electrons near electrons, which ultimately is not so great because they're all negatively charged and they don't really want to be near each other. So as they try to escape, we start to see different geometries basically form. So molecular geometry, again, is the 3-dimensional arrangement of our atoms and molecules. We can really kind of predict it from drawing our Lewis structure. And really, when we do draw our Lewis structure, what we're really looking at always when you do geometry, it's always the central atom. So It is always the central atom that is the most important when you are doing geometry. And in some cases, you may have more than one central atom, but each central atom individually is what you should look at. Personally, I think one of the easiest ways to do it is to look at the central atom, and you really are looking at two things. You're looking at how many electron pairs there are around the central atom. And the other important thing really is how many bonds you got going on there. So how many bonds to the central atom, how many electron pairs there are around the central atom. And depending on what the answer is to those two questions, you will have a certain geometry associated with that based on how many electron pairs and bonds there are. The idea of this approach is, as I mentioned, it's about the valence electrons, and ultimately electrons are negatively charged. So even though they have to sort of be near each other, they're both negatively charged, which means ultimately they're always trying to get away from one another. So they are trying to get as far away as they can from each other, but they are sort of tied to the nucleus. They can't completely escape. So what that does is, as I mentioned, as they try to escape from each other, everybody else that's attached and sort of locked into place will move accordingly. And what we end up getting is some different geometries that we see for molecules. So valence shell electron pair repulsion model, hence the abbreviation there, is the sort of theory and bonding theory here that we use to help us identify geometry. It accounts for the geometrical arrangements that we see, based again on the central atom and how many electron pairs there are around it. It's really basically broken up into two categories. One where the central atom has no lone pairs. So frankly, that means when you draw your Lewis structure, no dots on the central atom. Yeah. And one where you do have lone pairs on the central atom, which basically means when you draw your Lewis structure, you see dots on the central atom. And depending on if there are dots there or no dots there, will give us some different geometries depending on sort of the combination that we see. Probably the most important thing when you are doing geometry, and only when you're doing geometry, is really the first thing here. If you have a double bond or a triple bond, you should treat it as a single bond and also a single electron pair. So that's really important. You got the double bond action going on or the triple bond. When you go around and count up electron pairs, it counts as only one, and bonds, it counts as only one. So not just that it counts for a one bond, but it also counts as one electron pair. The idea there is the double bond and triple bond is effectively working as like one unit. So it was working as one big sort of electron pair unit and one bond that's sort of happening. So only in geometry, and when you're doing geometry, double bonds, triple bonds count as one electron pair and one bond. The second one, not so consequential here, but pretty much if you draw a resonance structure and you apply this geometry approach to any of the pictures that you drew, in most cases, if you drew the pictures correctly, you'll end up with probably the same geometry, regardless of sort of what resonance structure you shoot with. And even if you drew one where you did like the expanded octet, like we just did a second ago with sulfate, you'll end up with the same geometry as well as the one without the expanded octet versus the one with the expanded octet. So let's start with really the simplest molecules you could have in terms of geometry, and those are really diatomic molecules. So pretty much diatomic molecules are the simplest geometry you could have. Because they are diatomic, frankly, it is always going to be linear, because basically the only place you can put 2 points, right, straight line to each other. It doesn't matter if it's a single bond, doesn't matter if it's a double bond, doesn't matter if it's triple bond, doesn't matter if the same element or different elements. The geometry here will always be linear. So you essentially can just put linear and move on with your life. The better things to happen and all that kind of stuff. In this case, really, there is no central atom. So usually we don't do kind of electron pair geometry and molecular geometry for this. We just kind of say it's linear. Usually for both of those other ones, we kind of need 3 or more atoms sort of involved. So usually it's just a plain out linear to geometry that we go with these guys. Now that'd be awesome if everything was that easy, but it's not, obviously. So let's go through some examples where we do have some different things occurring. Our first example here is an incomplete octet, beryllium chloride. Once again, we want to focus on the central atom right there. And personally, I would count up the number of electron pairs. So when you're counting up the number of electron pairs, it doesn't matter if they're bonding electrons or non-bonding electrons. They could be dots or lines. It's the total number of electron pairs. In this case, we would have 2 electron pairs. And we also want to know the number of bonds, which in this case would also be 2 as well. The number of electron pairs that you count up when you look at your Lewis structure really is the thing that we use for the electron pair geometry. So something with 2 electron pairs, the electron pair geometry name would be linear. And basically 2 electron pairs and 2 bonds, the molecular geometry name would also be linear as well. So what is happening in this case is, frankly, these electron pairs here on each side decide, I want to get as far away as possible from you, right? So they basically go on opposite ends of the central atom. That is as far as they can space themselves out. And they end up basically becoming linear as well. It has a bond angle of 180 degrees. And again, that's pretty much as far apart as you could spread everybody out for. The next sort of geometry involves a central atom that has 3 things attached. And in this particular case here, if we did the number of electron pairs, once again, we look at the central atom. It has 3 electron pairs. The number of bonds here is going to be 3 as well. So once again, something with 3 electron pairs, the electron pair geometry name is what is known as trigonal planar. And some people call it triangular. The molecular geometry name will also be pretty much the same. It will be trigonal planar as well. So what happens in this particular case is we have these 2 guys here. They're trying to get away as far as possible from one another. But we also have that 3rd bond there. So he's coming along for the ride. So as they tilt this way, the 3rd guy kind of goes straight up. And what it ends up making is a bond angle of 120 degrees. And why it is referred to as triangular, it makes a triangle basically. Yes, it makes a triangle type geometry that happens. Basically, the best that these 3 guys could do, because we have the extra bond, is basically spread out just like that as far away as they can from one another. Obviously, with the lack of the 3rd bond in the previous one, they're able to get straight across from each other. But again, with the added addition of the 3rd guy, he's got to kind of move with them, and they're only able to get out about 120 degrees apart from each other in this case. Any questions on that there? Next sort of example is a central atom with 4 things attached. And here we have methane. So the number of electron pairs around our central atom right there is going to be 4. Number of bonds is also going to be 4 in this case. And again, something with 4 electron pairs, they're going to try to spread out as far as they can. Once again, because there's 4 of them kind of hanging out there, we will get an electron geometry, I'll just call it EG, of tetrahedral. Not too many books use tetrahedron anymore, but books used to. The molecular geometry name here will also be tetrahedral. Once again, with the addition of that fourth sort of bond there, as one moves around to get away, the other's got to move in accordance. And the best that we could do is a bond angle here of 109.5 degrees. Kind of makes like a triangle on the face and a little pyramidal action sort of happening there on the bottom. It allows them to get about 109.5 degrees away from each other in this particular case. Any questions on that there? Now, some of our expanded octet action here. So these might be some we're not familiar with. Here we have a central atom, and the number of electron pairs is going to be 5 in this case. The number of bonds here will also be 5. Something with 5 electron pairs around the central atom. The electron pair geometry is going to be triangular bipyramidal. Because these are all really bonded pairs as well, the molecular geometry here will also be triangular bipyramidal. There are actually 2 bond angles that develop here. There is a 90-degree bond angle right about there, 90 degrees. And there also is basically like our triangular, our trigonal planar, our 120-degree triangle happening as well, going through there, the center. So these are also sometimes referred to by their positions. This is equatorial, which is sort of on the equator there of the 3 dimensions. And these are axial positions. We're not going to do too much with that, but occasionally it does sort of come up as well. So once again, both the electron pair geometry name and the molecular geometry name here for this one is triangular bipyramidal. That obviously is in our expanded octet where we have 5 electron pairs, total of 10 electrons around it. The next sort of expanded octet geometry is one where we got our 6 electron pairs around it. And again, looking here, number of electron pairs going to be 6. Number of bonds going to also be 6. Something with 6 electron pairs around it. The electron pair geometry name is octahedral. And once again, they're all bonded pairs, which means the molecular geometry name also going to be octahedral here. This has bond angles of 90 degrees, so a little right angle action sort of happening there in this particular case. Up to this point, when we look at the electron pair geometry name and the molecular geometry name, are they different in any of the ones that we did? They're not. They're exactly the same. And they're exactly the same because in this case, they are all bonding electrons, which means as the electron pairs move, so does the atoms, right? They move accordingly with them. And that means that we end up with always the same name for both of those geometries. So whenever you draw a Lewis structure, you got no dots on the central atom. Both the electron pair geometry name and the molecular geometry name should be the same because basically the same electrons are moving with the atoms, which means the overall shape of the molecule will end up as those electrons move. It is really only when we start introducing non-bonding electrons to the mix that the molecular geometry name actually starts to change and we start to see different geometries. That's for 2 reasons. One reason is we get different interactions between different types of electrons. We get bonding electrons, non-bonding electrons in play. The other reason why we get the overall shape that changes is there's no longer an actual atom there that's moving around with the electrons. So it has a little bit more space to sort of move around, a little bit more space to try to spread out and get away from each other. And the name that is affected is always the molecular geometry name. So the molecular geometry name, as we introduce non-bonding electrons to the central atom, is the name that changes. The electron pair geometry name stays the same. So regardless if you got, non-bonding electrons and bonding electrons, there's still a certain amount of electrons around the central atom, but is that overall shape name or molecular geometry name that changes. So let's talk a little bit about that. There's really three types of electron interactions that could happen, and there's kind of good to bad in terms of those interactions. Sort of the best situation is basically what we just talked about, bonding electrons near bonding electrons. So lines near lines, you know, they're happy-ish in that situation. They're not really too upset. They get a little bit more upset when we get dots near lines. So when we get some non-bonding electrons near bonding electrons, they do not want to be near each other as much. So they do kind of repulse a little bit more. They're able to do that because, frankly, the non-bonding electron is not tied to an atom. Yeah, so it kind of has a little bit more room for movement. So it's able to kind of get away a little bit more. The worst sort of interaction you could have is when you get some non-bonding electrons near some non-bonding electrons. Neither one of them are tied to an actual atom. They can get away from each other as far as possible. And again, as those non-bonding electrons start to move, the overall molecules and the bonds that are there will also start to move. And again, that is why we see a change in the molecular geometry name. Any questions on that there? So let's take a look at an example here. This is sulfur dioxide. And if we look at sulfur dioxide has, in terms of the number of electron pairs around the central atom, it has 1 electron pair. The dots are 2 electron pairs. The double bond is 1 more electron pair. So it has 3 electron pairs. So when we're doing geometry here, the double bond is going to count as 1 electron pair. The number of bonds here is actually going to be 2 only. The single bond is 1, and again, the double bond counts as only 1 bond in geometry. As I mentioned before, the electron pair geometry name doesn't really change. It is based off of the 3 electron pairs, and we saw that earlier. Something with 3 electron pairs is our trigonal planar. But now we have some different interactions happening. If we look at the sulfur there in the middle, we got some bonding electrons near bonding. We got some non-bonding near bonding electrons. So with the lack of that third sort of bond, and now it's non-bonding electrons, everybody's able to get a little bit further away from one another. And we end up with a molecular geometry that we will roll with in this class as angular. Now, some people call it bent angular, and some people just call it bent. Yeah. The reason we're going to go with angular is there is a difference between bent and bent, if you use bent for both of them, and the difference is in the bond angle that we see there. This would be a bond angle of less than the 120 degrees. So it's a bond angle less than what we see in the traditional trigonal planar bond angle of 120 degrees. So we will use angular here. But again, sometimes books will use bent angular, and maybe your lab manual may even just use bent, and some people will just use bent for that one. But there is sort of a difference. We will see bent in just a second, and it has a different bond angle sort of associated with that. Any questions on that there? Next one would be NH3. And if we look at NH3 here, we got, in terms of electron pairs around the central atom, we have 4 electron pairs. And again, 1, 2, 3, and 4 electrons. In terms of bonds here, we have 3 bonds. So once again, something with 4 electron pairs, the electron pair geometry there is still going to be tetrahedral, as that is what happens when we have 4 electron pairs. Once again, unlike a traditional tetrahedral where we got 4 bonds happening there, we have that empty space there essentially filled by the non-bonding electrons, going to give everybody a little bit more room to kind of move about, and we will end up with a geometry known as trigonal pyramid. And as you can imagine, makes like a triangle and sort of a pyramidal shape on the bottom. Yes. The electron pair geometry that describes just how the electrons are arranged around central atom is still tetrahedral because there's 4 electron pairs. but the overall shape of the molecule, because it's missing that fourth bond, allows it to kind of move a little bit more than the traditional tetrahedral arrangement, and we end up with a geometry that is known as trigonal pyramid. Is possible. Tetrahedral in terms of molecular geometry would have actually 4 bonds. So they would all be bonding electrons like we saw previously. But when we lose that sort of fourth bond and it's replaced by non-bonding electrons, it gives us more trigonal pyramid type of shape. The bond angle is less than the tetrahedral bond angle of 109.5. As you can see here, it's actually 107.3. So it is a little bit less than what we normally see with the traditional 4 bonded tetrahedral arrangement. Now let's take a moment here to talk about 2 names that we just talked about before. That is trigonal planar, right? And this is trigonal pyramid. On an exam, you should write what it is, not just lay up trigonal and let me choose, because I'm going to choose an X, yes. Nor should you write trigonal. Clearly that is planar or pyramid or something like that, yeah. So make sure you choose, don't let me choose. As I mentioned, I failed chemistry, so that would not be a good choice to let me choose, yeah. So make sure it is different. You can't just lay up trigonal and hope for the best. The truth hurts sometimes. It's okay. I did. It's all right. There's nothing wrong with that. It happens. Happens to the best of us. All right. So another example here is a central atom. Yeah. Is what a covalent. These are all covalently bonded, so they're all sharing electrons here in this case. Yeah. So this type of geometry is really only applied to covalently bonded guys, not really ionic bond and stuff like that. Because here we're sharing electrons, so as they share electrons, they move around with each other. Other questions? Yeah. Yeah, and the names as well. Yeah. Other questions? So I think the bond angles you should know. Maybe it'd be like an extra credit question, but you definitely need to know the names for sure. Yeah. So I'm gonna say officially you should know the bond angles, but I think how it might show up might be more of an extra credit type question. Yeah. But definitely you need to know the names of the different geometries. All right, next one is a central atom where we have a number of electron pairs here around our oxygen is going to be 4. So 1, 2, 3, and 4. In this case, we have though only 2 bonds. So something with 4 electron pairs, once again for the electron pair geometry, going to be our tetrahedral. In this particular case, we actually have all 3 horrible interactions happening at once. If we look at the oxygen there in the middle, we have bonding near bonding, which is not too bad. We got non-bonding near bonding, which is getting worse. And now we have non-bonding near non-bonding electrons, which is sort of the worst interaction you could have. Because those non-bonding electrons are not really tied to a bond or anything like that, they basically decide, I'm going to go as far away as possible from one another. They obviously can't go too far away because they are attached, the other guys, to some bonds. So as those guys go up, the other guys go down. And what we get here in terms of the molecular geometry is what is known as bent or V-shaped, which is why water is typically drawn like this. Yes, bent or V-shaped, basically. The bond angle here is going to be less than 109.5 degrees. As you can see here, for water is 104.5. So this is what I was talking about earlier with our angular. The angular is less than 120. So it's like $1.15 or something like that in terms of the bond angle, 117 depending. This one is like really 104. So there really is a difference between sort of the angles that we see on both of those. So once again, for us, 3 electron pairs, 2 bonds will be angular to make it different than this one here, which is bent or V-shaped, which is again less than 109.5. Any questions on that there? Yes. You could do bent, or you could do V-shaped, or you could do bent or V-shaped. They would all be perfectly good. Yeah. Because as I just said, we're going to use angular for the other one, so I'll know you're doing the correct one in this case. Yeah. Other questions on that? Okay. Now we're going to get into some of our expanded octet geometries that have non-bonding electrons around it. So an example here would be XeF2. If we go to our central atom, the number of electron pairs is going to be 5 in this case. 1, 2, 3, 4, and 5 electron pairs around the central atom. In terms of bonds here, we got only 2 bonds. Once again, the electron pair geometry is going to be based off of the 5 electron pairs. And our electron pair geometry is going to be triangular bipyramidal. At this point, what happens is we have all these non-bonding electrons, but pretty much kind of goes this way, and this way. The result of that is our bonding guys actually end up spreading out opposites of each other. And it actually becomes a molecular geometry of linear. So it actually ends up being linear in this case, as our non-bonding electrons kind of fan out in a triangle type of shape. And that allows our bonding guys basically to end up on opposite sides of each other and gives everybody as much space as possible from one another. It gives the bonding and non-bonding guys some space between each other. Our bond angle here is, because it is linear, it is a bond angle of 180 degrees, just like our normal sort of linear bond angle happens here. So 5 electron pairs and only 2 bonds. Electron pair geometry, trigonal bipyramidal. Molecular geometry going to be linear. Next, expanded octet with some non-bonding electrons sort of happening here is in a deal where we have around the central atom, once again, 1, 2, 3, 4, 5 electron pairs. And in terms of bonds here, we got 3 bonds happening. So in terms of 5 electron pairs and 3 bonds, once again, our non-bonding electrons are going to kind of go this way. It's going to allow our bonding guys to kind of spread out. And as you can see here, it makes a shape of T-shaped. So again, our electron geometry name will once again be triangular bipyramidal because of the 5 electron pairs. The geometry, molecular geometry that we end up with here, going to be T-shaped, as it again makes basically a T, as you can see here, in terms of the bonding guys. The bond angle here is going to be a little less than 90 degrees, even though it kind of looks like a pretty straight 90 there, but it will be just slightly less than 90 degrees on our T shape. Any questions on that one there? Again, we see our, yeah. So here's the deal. For the most part, in terms of bond angles, if it is all like we did at the beginning, bonding, and they're all bonding electron pairs, the bond angles will be exactly what they were as we went through them. When we introduced with the same number of electron pairs, guys that have non-bonding electron, the dots, most people will just go with it's less than that normal bond angle. So really the bond angle goes with the electron pair geometry. And then as you introduce sort of the non-bonding electrons, it's usually acceptable just to go, it's a little less than the normal bond angle that we see because it has those non-bonding electrons and give it a little less. So in this case, the bond angle here is like a 90. So it'd be a little bit less than 90. Previously, like when we did the tetrahedral one, the tetrahedral bond angle was 109.5. When we got like our bent or V-shaped or trigonal pyramid, it's a little less than 109.5. So it's really based on electron pair geometry. And when you introduce the non-bonding electrons, most people don't want an exact number in most cases for this type of deal. They just kind of do less than that one. Other questions? All right, so continuing to roll with more expanded octet, the fun of expanded octet. I like the little move on that. That was good. Here we got, once again, electron pairs around the central atom. So we're looking right there. We got 1, 2, 3, 4, and 5 electron pairs. In this case, we have, in terms of bonds, 4 bonds, 1, 2, 3, 4 bonds. So as we've been talking about, once again, our 5 electron pairs for our electron pair geometry going to be our triangular bipyramidal. Here we do have the non-bonding electron pair there. So what's going to happen is that non-bonding electron pair is going to kind of go away. These guys are going to spread out. And as you can see, it makes like a seesaw type of shape. And the molecular geometry here is seesaw. Some people will also call this a distorted tetrahedral. If you find an old book, they will sometimes call it that. So I think all the new books use seesaw, but occasionally distorted tetrahedral will pop into play. And it's basically the same thing as this one. In terms of our bond angle here, once again, it's going to be based off of really the bond angle that we kind of see going on in this sort of geometry here. So it'll be a little less than the 120 and a little less than the 90 degrees that is happening in this case. Again, the 90 degrees sort of coming this way and the less than 120 sort of happening in that area. Now we're left with just 2 more to go, I think, in terms of expanded octet. And now we're going to get into our 6 electron pairs around the central atom. So XeF4 electron pairs around the central atom is going to be 6. And in terms of bonds, we have 4. And once again, our electron pair geometry will be based off of our 6 electron pairs. So that is going to be the octahedral arrangement. Here we have our non-bonding and non-bonding interaction, which are going to try to get away from each other. As it does in this case, it actually moves our bonded atoms into really the same plane and making a square shape here, basically. Hence the name square planar is sort of the overall geometry that we get as those non-bonding electrons move out, moves the bonded guys into a same plane and square shape. And our molecular geometry here going to be square planar. And again, our bond angle here will actually be 90 degrees because basically it does make a square, basically, all the guys that are bonded. Our last geometry here with our expanded octet that we go to is going to be 6 electron pairs and actually 5 bonds sort of happening in that case. And that is a guy that looks like this, BRF5. So once again here, electron pairs around the central atom going to be 6, 5 bonds and 1 non-bonding electron pair. Our bonds here are going to be 5. That is again going to give us our octahedral geometry for our electron geometry. Our molecular geometry, what's going to happen is it's going to make, again, kind of like a square and pyramidal type of shape happening coming down, or somebody standing on their head. One of those 2 things happening there. And the molecular geometry here is going to be square pyramid or pyramidal. Again, bond angle here would be less than 90 degrees in this particular case. Any questions on this? What is the best way to do geometry? Frankly, it is just to memorize it, right? Most people cannot visualize 3 dimensions in their head. You know, I can't either. But most people, this is sort of the easiest way to do it. Number of electron pairs, number of bonds, and just know this many electron pairs is our geometry name. And obviously the corresponding number of bonds will get you there. As we see with all these examples here that we did that have non-bonding electrons around the central atom, it is those non-bonding electrons that change the overall shape of it. Once again, because they are not attached to an atom, gives a little bit more room for everybody to get apart, which is ultimately, I guess, the goal of what they're trying to do is get away from each other, but they can't escape. So they try to get as comfortable as possible. to energize, and based on energy is really what they're doing. So as they kind of move around from each other and try to get as far apart as possible, they're actually minimizing the overall energy of their compound and their bonds that are happening and trying to make it a little bit more stable is essentially what's happening. Here's a table similar to one that you have in your book. And again, number of electron pairs, number of bonds is a good way to do it and would be my recommendation. So as was the earlier question, you do need to know both of those names, electron pair geometry name and molecular geometry name. In terms of the bond angle, like I said, it's probably good to know, but it'll maybe be like an extra credit type question. But so you do need to be able to obviously draw Lewis structures and give the geometry. Any questions on any of that there? Okay. And clearly we don't have time for hybridization today, I think. We will lay it up there, I think, for today.